So we'll do some simple questions so that you get more accustomed with the three-phase systems. Here, if in ACB sequence VAN is given as 100 angle minus 20 degrees, then find VCN and VBN. So what did we learn? If the sequence is given as ACB, then if this is some theta angle, then this is going to be theta minus 120 degrees, and this you can write as theta plus 120 degrees or theta minus 240 degrees. Now in the given question you have theta is minus 20 degrees. So then what will be VCN? The magnitude will be same 100. Angle will be theta minus 120. Theta is minus 20. So minus 20 minus 120 degrees. You're going to get 100 angle minus 140 degrees. Then what about VBN? This is going to be 100 angle minus 20 plus 120. So you're going to get 100 degrees. So if you draw in the phasor form, this is 0 degrees, right? So minus 20 is going to be like this, minus 20 degrees, then at minus 140 degrees, right? So this is minus 140, so that this angle is 120 degrees. We have VCN. And finally, at 100 degrees, this is 100 degrees, we have VBN. Okay, so we have to take care about the given sequence here. The next question is find line current delivered to the load 10 plus J8. So here the load is 10 plus J8. You can see that this is in star connection. Both the source and the load, they are in star connection. Okay. Now when a three-phase system is given, you can get a single phase equivalent if it is a balanced system. Remember, it should be a balanced system. So now what is the neutral point here? This is the neutral point. Now this is a balanced source. All the voltage magnitudes are equal and all of them, they have a 120 degrees phase shift. Now what is the condition for the load to be balanced? All of the impedances should have the same values, which is the case here. So this point also will be neutral and these both will be at the same potential. Once they are at the same potential, then we can consider both of them to be the same point and we can draw the single phase equivalent. Okay. So what will be the single phase equivalent? You will have the voltage source 110 angle 0 degrees. From here there is one more impedance 5 minus J2 and here there is the A terminal. Here we have 10 plus J8. Okay. So we drew the single phase equivalent or the single phase only because both source and load are balanced. Okay. So now what is the actual quantity that you need to find out? The line current. So here line current and the phase current are same for a star connected load. So this is the load current. So this is what we have to find out. So what will be IL here? This is equal to the phase current, which is equal to the voltage 110 angle 0 degrees divided by the impedance. Here we have a series combination. So 5 minus J2 plus 10 plus J8. Thus if you calculate, you're going to get 6.81 angle minus 21.8 degrees. Okay. So now this is what? This is only for phase A. Okay. So that means this is IA, only phase A. Okay. We want other phases as well, other line currents as well. So the other line currents will be also same. The magnitude will be same. What will be the magnitude? 6.81. And what will be the phase? Phase we can get from, this is if it is minus 21.8, B should be lagging by, if nothing is mentioned, we take the ABC sequence. So B should be lagging A by 120 degrees. So minus 21.8 minus 120 degrees. So what are you going to get? 6.81 angle minus 141.8. What about IC? This is going to be minus 21.8 plus 120 degrees. So this is going to be 6.81 angle 98.19 degrees you're going to get. Okay. In the next question, we have a balanced ABC sequence star source with VAN is equal to 100 angle 10 volt is connected to delta balanced load of 8 plus J4 ohm per phase. Calculate the phase and line currents. So here you can pause the video and you can first try it out for yourself. Okay. So what is the solution here? The source is star connected. Okay. So that means the source is going to be like this. Now what about the load? This is going to be delta connected. And you can see that the source is given as balanced ABC sequence and the load is also balanced. Okay. So we can convert this delta load into a star load and we can draw the single phase equivalent. Otherwise, we can also do one more thing. This will be the A line. This here is the B line and here we have C line. Okay. So now what will be the voltage available at each of the phase of the delta configuration? This is given by the line voltage. Now what is the given voltage here? It is given VAN. So when they say that it is between A and N, it means it is the phase voltage. Okay. So here we have given phase voltage is equal to VAN is equal to 100 angle 10 degrees. So what will be the line voltage? VL will be root 3 times into 100 will be the magnitude. And what will be the phase relationship? In a star configuration, the voltage leads the line voltage leads the phase voltage by 30 degrees. So here you're going to get 10 plus 30 degrees. Okay. So you're going to get 100 root 3 angle 40 degrees. So this is the voltage available across the load. So okay. So now we want what? Phase current as well as line current. That means this will be the this will be the line current and this will be the phase current. Okay. So we will mark the terminals also here. This is A, this is B and this is C. So where will the IAB current flow? IAB will flow like this and this is IBC and this is ICA. So therefore you can get IAB is equal to the voltage, that is IAB is this, right? So the voltage across this will be VAB. So VAB divided by 8 plus J4. So this is going to be 100 root 3 angle 40 degrees divided by 8 plus J4. If you calculate, you are going to get this value to be 9.36 angle 13.43 degrees. Once you find out IAB, you can simply find out IBC and ICA. Okay, so IBC will be the same magnitude, but the phase will be 13.43 minus 120 degrees. And similarly, ICA will be equal to 19.36 angle 13.43 plus 120 degrees. Okay, so these are all the phase currents. We also need to find out the line currents. So the line current IL is equal to, we will find IA. Okay, so what will be IA? This will be equal to root 3 times the IAB value. And what will be the angle? In the delta configuration, the current will lag the phase current. The line current will lag the phase current by 30 degrees. Okay, so root 3 IAB will be the magnitude and the angle will be the angle of IAB, which is 13.43 minus 30 degrees. So this you are going to get 33.54 angle minus 16.57 degrees. Okay. So from here we can again find out the other line currents. So IB will be the same magnitude, 33.54, angle will be minus 16.57 minus 120 degrees, and IC will be having the same magnitude and the phase will be plus 120 degrees, minus 16.57 plus 120 degrees. So these are the line currents. Next question you have, a 3-phase balanced star load draws 5.6 kilowatts when line voltage is 220 volt and line current is 18.2 amperes. Find the power factor of load. Okay, so this is a very direct question. What are the information that is given? So it is given that 3-phase load will draw 5.6 kilowatt. That means whether it is 3-phase load or single phase load, it is going to be the 3-phase load, P 3-phase, okay, because it is given in watts. So this is going to be 5.6 kilowatts. What else is given? The line voltage is given as 220 volt and the line current is given as 18.2 amperes. We just have to find out the power factor. So what is the 3-phase power? This is equal to root 3 VL IL cos phi. So here we know all of the values except cos phi. So what will be cos phi? This is equal to 5.6 into 10 cube because it is given in kilowatts divided by root 3 into 220 into 18.2. Okay. So the final answer you are going to get 0.807.